Good day. We've got a webinar today on the operation and maintenance of safety instrumented systems. Let's begin. So, just a very quick introduction. We'll keep it brief. We are xSeriCon. Who are xSeriCon? We're a safety consultancy. We specialize in safety studies, functional safety, alarm management, HAZOP, etc. My name's Dr. Joe Wiggers. Welcome. It's great to have you on board. I'm a chartered mechanical engineer, and I've been working with xSeriCon for a little bit over a year as a senior consultant. Can I introduce my colleague, Dr. Peter Clark?
Good morning, everybody. This is Peter Clark. I'm the Managing Director of xSeriCon. Thank you very much for joining our webinar today, and we look forward to hearing your questions and feedback afterwards. Thank you, Joe. Please go ahead.
Great, thank you. Just points of order. I see that you've all, most of you have your microphones muted. Be grateful if you could keep your microphones muted during the presentation. We would really love to hear your questions and feedback. So we'll make time at the end for that. If you want to kind of have a record of any question or any topic you want to talk about, if you type it into the messages, then we'll be able to pick it up at the end. Okay. So, as I said, today we're going to be talking about operation and maintenance of safety instrumented systems. We have a number of topics that we want to talk about, but if there's anything that you feel that we've missed, or if you've got any questions, as I say, please do ask at the end. And if we need more time, we can maybe hold another webinar. If you have ideas for other webinar topics, please do send them to us, because we'd love to hear what it is that you'd like to learn more about. Operations and maintenance. Well, I suspect that most of you will be safety engineers, and safety engineers get very involved in the design and implementation of safety systems. It's a very time-consuming, energy-intensive process, and once we've made sure that we have an unsinkable project, we can hand over to operations and our job is done, right? Well, obviously, this is a picture of the Titanic, and we realize that that isn't the case. So what do we need to do to make sure that during the lion's share of the life of a project, which is operations, the safety is maintained? We'll make some reference to a few past examples. Other than this, not the Titanic. I will make some references, particularly to the Flixborough disaster. I imagine that some of you will be familiar with it, but just in case you're not, I'll just give you a brief introduction. There was a tragic explosion. There were 28 were killed. This was a chemical plant producing caprolactam in the UK. The circumstances that led up to it were an alteration to the plant in which they had to bypass a leaking reactor vessel. So a while after the bypass was implemented, there was an explosion which caused an incredible amount of damage. So as I say, I'll be bringing that topic up as an example several times through our talk today. So if we don't launch and forget, what should we do? Well, functional safety requires a life cycle approach. So the standards, all the different standards, the family of standards under IEC 61511, 61508. Under 61508, we mostly look in the process industry at 61511. Thank you, Peter. Our talk about a safety life cycle. And the safety life cycle goes from risk analysis to the design of the safety system and its realization, and then it includes operations. And the important thing about the life cycle concept is that there is scope. You'll see the arrows on the right-hand side here to revert to earlier stages in the life cycle, so as to be able to revisit as necessary the risk analysis and the SIS design. The focus on this is to make sure that the safety that was designed into the system at the beginning will be maintained throughout the life of the plant. So looking at the life cycle periods that we just described, they break down into more specific tasks. In this webinar, we'll be focusing on operational. So we'll be looking at maintenance, management of change, audits and reviews, and there'll be more details as well with that. So IEC 61511 defines 5 activities that are required during operations. There's operator training, there's testing, maintenance, and performance measurement of the safety instrumented systems. There's the management of change. This is critical and was very critical in the Flixborough disaster. And there is functional safety assessment and audit activities. In order to understand how these activities are defined, it might be helpful to consider 3 questions that you need to ask during operations. First is, were our assumptions correct? So we put in a lot of effort to create a safety system, but we had to make some assumptions about how the safety system would work. And we need to ask the question, were we right? The second is, are people still informed? And the people, the operations, the maintenance, the managers who actually are responsible for running the plant, do they know what they need to know to operate the plant safely? And thirdly, has anything important changed? So looking at the question of are people still informed, I'll hand over to my colleague, Peter.
Yes, thank you, Joe. So competency management is one of the main requirements of the functional safety standards, and it is one of the most important techniques that's provided to help us control what are called systematic failures, which means failures in the safety system caused by some kind of human error. And making sure that everybody involved, as Joe just mentioned, that means managers, operators, and maintenance personnel, making sure that they all know what they're supposed to know is very important and must not be assumed, because we're talking about the entire lifetime of the plant, which could stretch over 30 or even 40 years. So just because everybody is properly trained and knowledgeable on day 1, you cannot assume that that will still be the case on day 1000. In the blue boxes on this screen, you can see various different aspects of competency that the standard says you not only maintain these areas of competency, but also be able to demonstrate it. So there has to be documentation. In fact, one of the blue boxes, the top right one, says documented records. The other things in the blue boxes, experience of the technique. That means the technique that is used to implement the SIS. So, for example, is it a programmable electronic system? Does it use pneumatic valves? Does it use what kind of transmitters does it use? And to have sufficient knowledge and experience about that, the technology involved in the safety instrumented system itself. Experience of the system or process, that means you need to know enough about the process that is protected. So whatever operation you're running, whether it be refinery or petrochemical or whatever it is. And in particular, you need to know what are the worst case scenarios. What is the worst thing that could happen if the safety instrumented system doesn't do its job? You need to be able to demonstrate that training has taken place, and this is ongoing training, as Joe correctly stated. Not just people informed and trained on day one, but that has to be maintained over a period of time. And we'll talk more about that on the next slide. Okay, and then knowledge of the technique, that is, again, the technique that is the technology involved in the SIS itself. And at the bottom, knowledge of regulatory requirements. So that would be any specific legal requirements that are local to the jurisdiction in which the plant is operating. Okay, Joe, can I move to the next slide, please? Okay, so specifically, what kind of, what's the purpose of providing this ongoing training? Well, as we know, people who run the plant, most of them sincerely desire to do a good job, but with the kind of incident that we're trying to protect against using our safety instrumented system, those kind of initiating events, the demands on the system may not happen for year after year, and they may never actually, or not for a long time, actually experience the plant conditions under which some kind of response on their part is necessary. So that's why it's necessary to not assume that they will remember all the details of the training they were given at the beginning. We have to reinforce it as well, because repetition of important messages is important, partly to help people remember, but also to emphasize the fact that management take this seriously as well. If you keep on hammering away at the same message, then there is a trickle-down effect that the shop floor workers realize, actually, yes, the managers really care about this. This is actually genuinely important. Other factors to consider, on the left side, it says out of date. So over time, the process changes inevitably. Changes are made, changes in feedstock, changes in design, changes in product slate. Equipment is replaced with new updated equipment. Procedures change, shift patterns change, manning changes. So things gradually become out of date, and you need to update and refresh training to make sure that it's always correct and appropriate. And then also there is staff turnover. People leave, new people come, and you need to make sure that the new people are going to be just as competent as the people who have been there for many years. What do we need to include in the training? Well, I'm going to focus on training on this slide for the operators and on the next slide for the maintenance personnel. So for the operators, moving down the left side of this slide, first of all, normal operations. They need to know what to expect to see on the screen. Now, we understand that with safety instrumented systems, normally the operator has nothing to do. They don't need to enter set points. They don't need to actively control it. They just need to monitor it. So they need to know what all that information on the HMI is actually telling them, so that they know when it's moving away from a correct or normal situation that might require intervention. The next box says permit to work. That is a reminder that any non-normal action relating to the safety instrumented system should be done only under the control of a permit to work. And that, in many plants, that includes applying bypasses to SIFs, to safety instrumented functions. The third box, cybersecurity. We're going to talk about this more later, but just very briefly, the operators need to be reminded how important it is to maintain proper cybersecurity measures and not to bypass procedures. Moving down the right side of this slide, the first box says SIF trips. This says, what do operators need to know or need to do when a trip occurs? It's very important that they capture certain pieces of information for follow-up and investigation. Every trip should be treated as an incident and it should be investigated. The root cause of it should be understood and analyzed and used as a learning, not only for learning, but also for data gathering, as Joe will explain later. The next box says SIS faults. When a fault occurs, hopefully an alarm will be raised. What do those alarms mean? And very often the operators don't actually know what the alarms mean. They don't know how or whether to respond. For example, if it says, communications fault alarm, redundant, channel alarm, power supply alarm, they don't know what it means. So they need to have guidance. They need to have documented procedures for what to do when SIS-related alarms come. And one other thing that's very, very important is normally the SIS includes a way for the operator to trip the functions manually. Not always, but in many cases. The operators must have clear instructions under what circumstances are they authorized to operate that trip without prior approval from management. Now, this is extremely important because operators know that when they press that big red button, the plant will shut down and it will start clocking up large costs of lost production. And they are naturally reluctant to do that because their job is to run the plant, not to stop the plant. And they know that questions will be asked, why are you costing us $1 million a day because you pressed that big red button? Why did you do it? They have to know when are they authorized to do that without having to refer it up to higher management in an emergency situation, so that they feel comfortable to know that it's okay to press that button under certain circumstances. Very important, because there have been many incidents. For example, 3 Mile Island incident in the US is one case when the operators should have shut down the plant manually, but they resisted doing so because they knew they'd get in trouble if they did. Okay, next slide, please. And this is the training that maintenance personnel need to be given and refreshed on a frequent basis. Moving down the left side of this slide, FSMP means Functional Safety Management Plan. So they need to be aware that the plan exists and what parts of it are relevant to them, particularly relating to, of course, maintenance and modification of the safety instrumented system. They need to know exactly what proof test procedures are needing to be implemented. Sometimes there will be different procedures for example, you could have a 1-year proof test and a 5-year proof test. So they need to know about the different procedures and when to apply them. They also need to know exactly what to do, what procedure to follow step by step, including, for example, applying bypasses, applying for the permit to work, making sure that bypasses are removed afterwards, and what exactly should be documented. Documentation of proof tests is extremely important. Password control, password management. In many cases, they will need to unlock or override something in the SIS requiring a password. So they need to know that that password must be protected. Critically important that it doesn't end up written on a yellow sticky note on the screen, which so often happens, because that's just an open door for a cybersecurity incident. At the bottom of the left side, restore procedure. So they need to know what to do exactly to make the safety instrumented system fit for purpose again, to put it back to its fully running state. And there have been incidents where accidents occurred because the SIS was in full working order, but a bypass was inadvertently left in place. Moving down the right side of this slide, disabling, bypassing, SIFs and tripping. Well, it says tripping, but hopefully not inadvertently tripping SIFs, so they know how to avoid causing an inadvertent trip. That information needs to be given to them, how to do it and when to do it, and how to document it. SIS failures and alarms, so they need to know what, again, similar to what we said about the operator, what to do and what to document when a failure occurs. It must be investigated, what all the alarms mean and how to respond to them. How long can you continue to operate safely when an alarm comes? That must be clearly defined. In fact, that should be defined in the safety requirement specification, or possibly in the design specification of the safety logic solver. Modifications. So if it is the responsibility of maintenance to do modification, although quite likely it will not be, with the possible exception maybe of changing set points, then they need to know exactly what procedure to go through. But most likely that should not be in the scope of the regular maintenance personnel, because that requires a management of change review in most cases. Even for modifying a set point, you should do management of change. And SIS event analysis, I think Joe is going to talk about this more later, but as I've said, you need to treat every trip as an incident, which needs to go through a full investigation to understand the root causes and the implications of that. So now I'm going to hand back to Joe for the next slide.
Thank you, Peter. Yes, and in terms of an example from Flixborough of people being uninformed, on the management level, the decision was made to bypass and how to bypass the reactor vessel was made 5 months after the last senior chartered mechanical engineer had filled the post of works engineer. They'd had an open post for 5 months. And so you saw that a decision was made with the inadequate information, and it was essentially a bunch of chemical engineers who made a decision and were not able to evaluate the potential consequences of their alterations from a mechanical point of view. So in terms of considering the effect of actions on the process from a safety point of view, it's really important that you have a culture in which every part of the expertise is presented from operations, engineering, designers, and so on. So we're going to move on to the question, were our assumptions correct? So you may be familiar with the process of determining how a safety instrumented system will work. Essentially, you start off by assessing the process risk. You look at any independent protection layers, any other things, say firewalls or other passive or semi-active measures which will mitigate that risk. You then design your safety instrumented systems. So for each risk, you design a safety instrumented function which will mitigate the risk further, and you aim to get down to the tolerable risk. So in that process, you make a lot of assumptions. You have to make assumptions about, in order to determine what the process risk is, you have to make assumptions about how effective the independent protection layers are. You have to make assumptions about how effective your safety instrumented function will be. And any one of those assumptions may prove to be incorrect. And it's vitally important that you evaluate those risks once you run into the operations phase. So, for example, you need to monitor your SIF demand rate. How often is the SIF having to activate? This is a proxy, an indication that your process risk may be greater than you initially assessed. And analysis of the SIF demand events may also highlight process risk events which you had not considered originally. You need to consider the availability of other independent protection layers. I mentioned passive ones, but there are semi-active ones. For example, there may be some credit may have been given for an alarm going off, which requires an operator response. But if the operator tends to not be in the right place to note the alarm or respond to it during the time that that alarm is most likely to go off, then obviously the availability of that independent protection layer is not adequate, and so it may not be as much of a risk reduction factor as you had counted on. Failure rates of your SIF. This is talking about failure rates of the hardware of your safety instrumented function. I'm talking about random failure rates. They may be different to that which you had accounted for. Obviously, the failure rates are derived from other uses of the hardware, and it may be that environment is sufficiently different that you're seeing different failure rates, or there may be some common cause failures which are causing it to fail more than you expected. You need to consider the SIL capability, and so, for example, systematic faults really is in this case is considered to be a question of did you get adequate hardware? Is it manufactured to good enough quality? Has the design been performed to the required standard? Whether are there errors, systematic errors, which are leading to your SIF hardware failing more often than you may wish. And another one which you may consider is not relevant is the spurious trip rate. And now, of course, spurious trip rates don't have a safety consequence, or do they? In terms of the performance measurement of your, say, safety instrumented system, it's actually really very important to keep an eye on your spurious trip rate, because even though a spurious trip is one in which the safety instrumented function trips the process when it didn't need to, and therefore you haven't compromised safety, it nevertheless may indicate that your safety instrumented function is failing more often than you had accounted for. And luckily for you, it failed in a safe manner. But it's important to document the spurious trip rate, because it gives you another chance to flag up assumptions that were incorrect about the performance of your safety instrumented function. Now, there's two parts to performance measurement of the safety instrumented system. The first, I think, most software systems come with detailed documentation capability, but of course it's part of the training, as Peter explained. It's important that the operators and maintenance personnel and others actually do their part in documenting performance measures. But the second part, I think, is probably a lot harder, which is the question of analysis. It's important not just to amass huge amounts of documentation of events, but it's really important to analyze those events and make sure that the lessons that can be learned from them are taken. So in Flixborough, this was actually there was an assumption that was made right at the start, which turned out to be not be the case. This was the finding on the Flixborough disaster, stated: no one concerned in the design or construction of the plant envisaged the possibility of a major disaster happening instantaneously, as opposed to escalating disaster. And essentially, the majority of the deaths that happened were because there was absolutely no warning, and it was not considered to be an instantaneous explosion as actually happened. And so it's very important that you question your assumptions as you go through your operational phase. Testing and maintenance. We maintain the plant to keep it running, right? Well, in actual fact, with a safety instrumented system, its maintenance and testing has another focus, which is a very important one. What's the purpose of a proof test? It's primarily, is part of that performance measurement, it's to check for failure modes that were not covered by your diagnostics. So your safety instrumented function may appear to be fine. And when you conduct your proof test, you want to find any failures which had not become apparent so far. So, for example, an important consequence of that is that you should test before inspecting. It'd be very easy, let's say, if you come across some corroded connectors on your safety instrumented function on your valve actuator, to quickly reconnect them, because how can you test them if the valve won't work? It's really important to actually test it first and find that the valve doesn't work, and then find out why and correct it. All SIF components need to be inspectable and testable. That might seem to be an obvious thing, but in Flixborough they had a lot of lagging, which covered a lot of the pipework and made inspection difficult. The most famous example of that is the Buncefield disaster, in which there was a level transmitter that was placed in the top of a tank in such a place that it could not be proof tested. And importantly, it wasn't working on the critical day, and nobody knew that it wasn't working. It's important to test your safety instrumented function end to end, if at all possible, because you need to check the whole system working as one. If that's not feasible, then you can break it up into sections, but it's important to make sure that the sections overlap so that you get as close to an end-to-end test as possible. Record keeping is really important and often overlooked, and it's important to develop procedures which inform the maintenance personnel what record keeping is required. For example, often they don't think to record which specific instruments were used during the test, and therefore it's impossible to trace back to the calibration of that test equipment. Another note is the usefulness of testing for questioning the assumption that was made during the design phase of proof test coverage. Proof test coverage is the percentage of dangerous faults which the proof test actually can discover. A proof test will not be able to discover all dangerous faults, though it might be able to discover most of them. But surprisingly, very frequently, proof test coverage in the design phase is assumed to be 100%, because the designers don't have access to any other value. And that is always going to be unconservative. It's always going to be the most optimistic value for proof test coverage. Another value that's useful to measure is proof test reliability, which is often confused with proof test coverage, but is a different measure. And that's the probability that proof testing is performed as per procedure, as it's expected to be performed. Now, that's not a constant value. It's, again, often assumed to be 100%, and you can assume that a big proportion of the time it isn't 100%. But also, it's important to note that it's not going to be a constant value. So the assumption may have been made from a similar plant in a different location, but it's been shown in the past that the proof test reliability between locations can vary significantly, even with the same operating company. In fact, it could be that proof test reliability is different according to shift. It certainly will alter over the longer term as personnel turnover. So this is an important measure to document. Okay, so we've talked about some of the things that you need to monitor as you go through the operating life of the plant. The mechanisms which the standards bring in to check that are functional safety assessment and audits. So the functional safety audit, I think we're all familiar with audits. In this case, is functional safety related, and it checks those procedures that are relevant, that they're up to date, properly implemented. A functional safety assessment is, I think, less well understood. It's harder to explain, but the best way we can think of describing it is to say that it's the objective of a functional safety assessment is to check that safety objectives are met. And there are two different stages that are relevant to operations. Stage 4 is defined in the standard as after a period of SIS operation. I'm going to highlight stage 4 because it's actually mandated. There are two stages in which FSA is mandated. It's stage 3, just before the risks are commenced, and stage 4 after a period of SIS operation. So this is actually, if you want your plant to be accredited to IEC 61511, you need to conduct a stage 4 FSA. And stage 5 is after modification of the SIS, and enough disasters have happened in the past that I hope that it's readily apparent how important it is that when there's modifications that the processes are followed through, and a good way of ensuring that they're followed through is to conduct an FSA, which will require an overview of that. Let's have a look a little bit more at what's involved in conducting functional safety assessments. So stage 4 is one which is looking at ensuring that assumptions are validated and assessed. So it's looking at procedures, safety, operation, maintenance, and emergency procedures, but not like an audit. It doesn't take them at face value. It looks at whether these procedures are fulfilling those safety objectives that were determined at the start of the project. So also it will assess competency in training, and again the focus is always on the safety objectives that were determined at the start of the project. Record keeping will be looked at, and the data and analysis arising from the safety instrumented system operations. Functional safety assessment can seem to be quite contradictory because it requires access to great depth of data, and yet it is a helicopter overview. It's looking at the whole overall system and considering whether the safety objectives are continuing to be met. At stage 5, after modification of the SIS, this is the other question: has anything important changed? And FSA is designed to ensure that, first of all, any changes have been assessed by a competent person to determine the impact. And After that has been done, it's looking at the returns to the previous FSA stages according to what's required. And that really depends on the type of change. Minor changes may not require as much rework as major changes, but it could include all the way back to the beginning, the hazard analysis. And there will be some if it does go back to hazard analysis, then there will have to be some rework of the SIL determination, the design of there might be some additional safety instrumented functions that are required. So you need to design, evaluate those, implement them, and test them. Let's talk a little. Oh, yes,
Joe,
Peter,
sorry,
please.
yeah, can I just jump in? Because unfortunately, I have to leave the call a little early today, and we are starting to run a bit short of time. So would it be okay if we just skip for a moment to the part that I'm going to talk about, and then when I'm done, you can come back and cover this part?
Sure, of course.
Sorry about that. So I'm going to talk about the management of change. We've mentioned it several times, management of change, extremely important. The focus is on change of the safety instrumented system, not specifically change of the process. So any change that is suggested to change the safety instrumented system. And that doesn't actually just mean the system itself, but also all of those underlying assumptions that were made during the design phase of the system. And these might not be particularly obvious. Just to give you one example, very often we assume during the risk analysis phase that we have alarms to which the operator can respond. And credit may be taken for those alarms and we say that the alarms are capable of reducing the risk. And therefore, the SIL rating of the safety functions can be reduced because we have alarms with operator response. But supposing we make some change, let's say we change the shift pattern, or we change from a manned to an unmanned facility, or we reduce the number of operators sitting in the control room, that may change the validity of that assumption that operators can respond to alarms. And if we now decide that operators cannot be assumed to respond to alarms, that may mean that the SIL rating of those safety functions has to increase, which might mean a change of design of the SIS or a change of something else like proof test interval in order to achieve the new SIL target. So in that way, a management of change study is required even when the change that's proposed is something you might call it soft, not related to hardware, something like manning situation. Occupancy, the second bullet point that's given on the slide, that's like we just said, if there's more people now in the danger area than previous, let's say we build another plant next door, another unit next door, so now there are more operators coming and going, the assumption that we previously made that the area is normally not occupied and therefore of low risk of causing injury to the operator in an incident, that might not be valid anymore. In fact, one study that I did a few years ago was when an offshore platform that had been originally designed to run in an unmanned state was now going to be changed to normally manned. And so we had to go through all of the HAZOP study, the risk assessment study, to determine how that changed the probability of injury to the operator in the event of a major incident. And we found that it did have an impact on the safety functions. Many of them had to be uprated because of that from, for example, SIL 1 up to SIL 2. A third example might be the feedstock. Let's say that we change the feedstock, maybe due to the aging of the plant, the aging of an oil well or gas well, for example, changes the operating conditions, maybe changes the throughput, or other factors like gradually the equipment deteriorates, heat exchangers get gradually less efficient as they get fouled over time. So all of that can impact And these are, you could almost say, unintentional changes or undesired changes, but they are changes nonetheless. So those ought to be assessed periodically to assess whether they will have an impact on the SIS as well. Okay, Joe, can I go to the next slide, please? Right. The other thing that the standard says we have to consider is decommissioning. Now, the standard, what it says about decommissioning is extremely brief and not very clear. But what I think it means is decommissioning or partial decommissioning of the safety system. It's not so much focusing on decommissioning of the process. So let's say, for example, we decide that part of the safety system is not needed anymore for some reason. We have to assess whether that will have an impact on the remaining parts of the safety system. Let's take an example. Supposing you've got 2 control rooms in your facility, but now you decide that one of them is no longer required. So you shut down that control room, which means now you no longer have an HMI, human machine interface, to operate the SIS in the old control room, the one that's been shut down. So now we need to ask the question, well, does that change the assumptions about the operability of the safety system? Supposing there's a power outage in the one remaining control room, does the operator still have the facility to shut down, to operate the manual trip of the SIS? Because it might have been that he was relying on being able to call the operators in the other control room to do it. And now he can't do that anymore. So we need to check if we decommission part of it, can the rest of it still work safely? And the other very important point is, if this means we need to modify the application software, which means, for example, the ladder logic software that is actually implementing the safety functions themselves, is it possible that that could have an impact on the remaining part of the software, the bit we want to keep? And it would be wise, I would say it would be pretty much compulsory, to revalidate the application software after doing such a change. And that's not a trivial task, very important task. Okay, next slide, please, Joe. Right. Well, no talk on safety instrumented systems, and especially on operations, is complete without at least a mention of cybersecurity. It is a massively important and underestimated topic nowadays. And we're not going to get into a big, long explanation of it, but I just want to make sure that it stays on our radar all the time. We need to be thinking about this all the time. And I've got a few kind of key take-home points on this. First of all, normally, a cybersecurity assessment would be done at an early stage of the project during the design phase, or maybe even earlier than that, which will specify certain cyber hygiene measures that need to be taken, such as firewalls and such as physical blocking of interfaces like USBs, password protection, and all the rest of it. Those must be maintained. You must make sure that those stay in place. So I would think that that's important to have a periodic audit to make sure that all those hygiene measures are still in place. Secondly, we need to keep on hammering the message about how important cybersecurity is. We need to keep on saying to the operators, do not plug in your USB into the workstations. Do not install unauthorized software. If you do, there will be serious consequences, and there must be indeed serious consequences if they do compromise cybersecurity. The third one is to make sure we're always keeping aware of new threats that are out there. The outside world, the bad actors out there do not stand still. They're always looking for new ways to get through. So you need to have a specialist or a consultant who's watching the situation and warning you about new threats that you need to be keeping aware of. And the fourth one is equipment vendors also may be issuing updates, for example, virus pattern updates. Maybe they're issuing patches to close vulnerabilities that have been discovered in their systems. So you need to pay attention to those, make sure that the updates and patches are validated, and if and when they are, then you should go ahead and install them and keep up to date on that. Joe, is this the point at which I hand back to you?
Yes, it is. I'm aware that we've overrun significantly, so I'll just talk about overrides. We've talked about overrides and bypasses. I think Peter's discussed them quite a lot. It's important to make sure that overrides and bypasses are actively managed. So it's about restricting access, password protection, we've talked about that, making sure there are permits to work. An important question is, have they been left in place when not required? One way to ensure that that doesn't happen is to actually make sure that they have timeouts. After a timer expires, you might sound an alarm, and often it's a good idea to have the alarm sounding after repeated timeouts, because if when you have change of shift, there may not have been handover on that. And or possibly even the SIF trips the process. And the importance of timeouts is because after a while, a bypass can become a convenience, so it doesn't any longer become a question of have assumptions been maintained, but it's become a question of have we actually changed the way that the safety instrumented system works. And the thing is that you can easily have a mentality where safety instrumented systems are seen as an inconvenience, and the problem is you have to protect against that. I'm not going to take too long talking about this because, as I say, we've overrun. Peter needs to leave very soon. So if you have any questions for us, I'll open the floor now for any questions. If you'd prefer to type in any question, I'm keeping an eye on the meeting chat. Okay, I'll highlight that we have another webinar which is coming up on Thursday, the 15th of December at the same time. It's preparing for functional safety assessment. If you enjoyed our webinar, we'd love to hear about it. So please do email us. If you have questions which you feel you can't quite phrase or you don't want to do it in a public forum, do email myself or Peter. We both receive the info@xSeriCon.world emails, so we'll be able to help you with that. We're really interested in understanding what other webinar topics would interest you, or is there something that you were expecting to get from this webinar which we didn't address? Then please let us know. Finally, I'll mention our software sellability. If you want to have a free trial of it, do contact us about that. I hope you enjoyed our webinar. I'll wish you all a good day, and I hope we'll hear from you again soon. Thank you.
Thanks, everybody. Yes, just echo Joe's comments there. Thank you very much for your participation. Please let us know if there's any other way we can support you. We have other materials available relating to today's topic and anything to do with functional safety. We have training materials available and other resources, and we can provide guidance and consultancy if you need that. So please feel free to contact us and discuss whatever you need. I think we can close there for today, Joe. So thank you very much, everybody. This webinar will be posted shortly on our YouTube channel, so you can catch up again and let your colleagues know if they want to watch it as well. That's all for today. Thank you very much, everybody, and goodbye.